Hello, good evening, everyone. For those of you who do not know me, my name is Vicki Sanchez. I am the Annual Funded Membership Director here at the Field Museum. I'm joined on screen tonight by Dr. Maria Valdes and Kyle Malone, if he shows himself in a second, who is our Annual Fund Specialist here at the museum. And I'm sure many of you have spoken with Kyle in the past, as he's always available to help. If you need closed captioning, I always say this first, just in case you need it. If you need closed captioning, please click the closed caption button on the bottom and the captions will pop up. But first, I want to start off by saying thank you to you, our museum members and donors. It's through your generous support that the research projects and the scientific work that we do here at the museum continue, and you'll be able to hear some of the stories that Maria is going to share tonight. And it's through your generosity that we're able to continue doing that great work, protecting our collection, going on different research projects, out in the field, whether it's here in the Calumet region or as far away as Antarctica. So again, thank you so much. Before we begin tonight's presentation, I just want to go through a couple of quick housekeeping tips. And that is, if you run into any kind of issues, please use the chat function and Kyle will help you on the back end. We are going to hold all questions to the end of the program. So please use the Q&A button if you have a question that you think of during the presentation. We don't want you to forget it later. And we'll make sure we get to it at the end. And if we don't get to all your questions, don't worry. I'll make sure that I get together with Maria over a cup of coffee and we'll make sure that we follow up and get the answers to your questions. So that won't be any problems. I'm really excited for tonight's presentation. We had Maria join us last year before she went on her expedition to Antarctica, and we invited her again tonight to share her experiences. And so I'm just going to do a quick intro. Dr. Maria Valdes is currently a research scientist at the Robert A. Pritzker Center for Meteoritics and Polar Studies at the Field Museum. After completing her undergraduate degree in geophysical sciences at the University of Chicago, she completed a master's degree in Earth and Planetary Sciences at Washington University in St. Louis, a PhD in geochemistry and cosmochemistry at the University of Brussels, Belgium, and a postdoctoral position at Cambridge University in the United Kingdom. She studies the history and the evolution of solar systems through the chemistry of meteorites, which she considers windows into our ancient past. And now to share her ongoing research with us tonight, I'll turn it over to you. Thanks, Maria.
Thank you so much. Let me share my screen here. I hope that's visible, and I hope I'm audible as well. All good, I think. Okay, thank you, Vicki, for that wonderful introduction. I'm Maria Valdes, as she said, and today I'm going to talk about my work using meteorites to study the origin and evolution of the solar system, as well as my recent Antarctic fieldwork. Last week downstairs, I had set up a table with meteorites at the Science Hub, and by the end of the session, my 5-minute spiel was pretty well rehearsed. I was going over the histories and the similarities and the differences between all the materials I had on the table. And then this one particularly inquisitive kid looked me dead in the eyes and said, "Yeah, but why do you do any of this?" And I was a little taken aback, but also, valid question, kid. And if I'm honest, it's a question that I often find myself wondering about my own colleagues here, as I'm sure they wonder about me. Why do we do any of what we do? So instead of giving you like a science-heavy lecture tonight, I want to focus on the why and the neat adventures that the why sometimes takes me on. So here at the museum, I consider myself a cosmochemist. Cosmochemistry, by its broadest definition, is the study of the chemical composition of matter in the universe and the processes that led to these compositions. The term cosmochemistry is modern in its origin, but the science can be traced back more than 200 years to a time when, for the first time, scientists realized that they were analyzing pieces of extraterrestrial matter. Cosmochemistry encompasses the study of the compositions of our solar system's sun, the planets, and their satellites, the many, many asteroids in the asteroid belt and beyond, comets, and all of the dust in between. And the overarching goal is to understand how we went from a vast molecular cloud made of hydrogen and helium and dust with contributions from different stellar sources 4.6 billion years ago to the solar system as we know it today. And astrophysicists and modelers have given us a really good story to work with. And the running story as of now, is that the solar system began with the collapse of a molecular cloud, and this may have been caused by shock waves from a nearby supernova. And the resulting increase in angular momentum formed a rotating disk, what we call a protoplanetary disk, nestled inside the molecular cloud. And at the center of the protoplanetary disk, a proto-sun began hydrogen fusion when sufficiently high temperatures and pressures were achieved. Meanwhile, the remaining gas and dust on the outside of the disk spread out, and over time, planets grew out of the protoplanetary disk via accretion, whereby micrometer-sized particles coalesced into centimeter-sized particles. Those coalesced into kilometer-sized planetesimals, and then those coalesced into planets. And any material that did not accrete into planets, didn't make it into planet form or into satellites, remains now in the solar system as asteroids, mostly in the main asteroid belt, orbiting the sun between Mars and Jupiter. So how has this story been supported by chemical data? What samples do we have available to us? There are, of course, sample return missions that have given us samples, such as the Apollo missions of the 60s and 70s, and the Mars 2020 Perseverance rover that's currently on Mars exploring Jezero crater and should return samples to us within the next 10 years or so. But these missions are rare, they're expensive, although they do provide one-of-a-kind information that cannot be obtained from other types of extraterrestrial material, and that's spatial context. But still, they're rare, they're expensive. So for the most part, we obtain extraterrestrial material from samples that fall to Earth on their own accord. Meteorites. Meteorites are fragments of asteroids that collide and break up in the asteroid belt, sending about 2 tons of material to Earth every year. I should say not all meteorites come from asteroids. A small fraction are known to be of lunar origin, and we know this because we can compare them to Apollo and Luna samples, and some do come from Mars. There are also micrometeorites. This is cosmic dust or interplanetary dust, and these are any meteorites that are less than 2 millimeters in diameter. These actually make up the largest portion by far of material that falls to Earth, about 47,000 tons of it every year. But as of now, it's still meteorites that we have derived the most information from. So an overview about meteorites, there are 2 fundamental types of meteorites. Chondrites, which are more common, they're aggregates of solar nebula dust grains, and achondrites, which are derived from larger asteroids, ones that got big enough and hot enough to have undergone partial or even complete melting and planetary differentiation early in their history. Planetary differentiation processes such as core formation and crustal formation. This group also encompasses meteorites from other planets, so Martian rocks are achondrites, for example. As remnants of the protoplanetary disk, meteorites are windows into the solar system's earliest history. They're sort of time capsules that record in their compositions the initial conditions of and the thermal and chemical processing that occurred in the protoplanetary disk. They record how and what kinds of material accreted together to form their parent bodies. And in the case of achondrites, They also record any igneous processes that occurred on the parent body, such as core formation and crust development, processes that didn't occur on chondrite parent bodies. Here at the museum, we have one of the world's largest, most important, ever-growing collections of chondrites and achondrites. The collection started with about 170 specimens as part of the natural history exhibit at the 1893 World's Columbian Exposition, and has since grown to about 15,000 individual specimens of about 1,500 different meteorites. So it's a really invaluable resource for cosmochemistry. Now, to circle back to the very inquisitive kid who inquired why I do things at the Science Hub, why do we do any of this? Everyone has their own niche and their own set of very pointed questions that they're aiming to answer. But for the most part, we're all working together toward developing clearer answers to 5 overarching questions in cosmochemistry. Those being, where did solar system matter come from, and what are the genetic relationships among solar system objects? Can we track the chemical evolution of differentiated bodies? Can we constrain the composition, evolution, and relative abundances of the components that accreted to form the Earth? What led to the rise of life on Earth? And how can we use all this information to guide future space exploration? Now, the same skeptical child who asked me why I do any of this also asks me how I know any of what I know. Again, great question. She's definitely going to make a really rigorous scientist one day. But basically, cosmochemistry utilizes many analytical methods, both destructive and non-destructive, both sample-based and remote being either telescopic or with spacecraft. And they all really need to be used in conjunction to get the most science out of precious samples and expensive missions. So continuing to find ways of combining methods is how we're going to build an ever clearer timeline of solar system evolution. Some of the non-destructive analytical methods that we use include orbital data. For example, data obtained from NASA's Dawn mission, which is a spacecraft sent up in 2012, I believe, and orbited the asteroid Vesta for about a year, collecting information about its surface composition and its topography. And then once we have actual samples in our hands, we can study their mineralogical and petrologic assemblages using non-destructive or minimally destructive microscopy and spectroscopy techniques such as X-ray tomography and fluorescence, scanning electron imaging and chemical analysis, Raman spectroscopy. These techniques offer context for data later obtained with the destructive techniques. These are ones that require partial consumption of specimens or full consumption of specimens, because studying their elemental and isotopic compositions often require cutting, grinding, homogenization of the sample into a fine powder. It's quite destructive, but sometimes necessary. We do this because, or we study the elements and the isotopes of these rocks because the behavior of elements in space is largely governed by their volatility, which we quantify by specifying the temperature or temperature interval at which elements change state from a gas to a solid during cooling. And so elemental compositions can tell us about the conditions under which a solid formed and where in the solar system, how close to the sun, at what temperature it formed. And the electrical properties of elements also control their behavior once they've accreted into parent bodies. So how they combine into minerals, how they dissolve in fluids, how they concentrate in magmas during melting, high temperature. But I want to concentrate for the next few slides on the isotopic compositions of meteorites, because this is what most of my work has concentrated on over the past few years. Now this is going to be like the only kind of sciencey slide. We'll get into adventure stuff after this, but the state of cosmochemistry is where it is right now, in large part due to the development of isotope cosmochemistry and its essential tool, the isotope mass spectrometer. The determination of the isotopic properties of extraterrestrial materials and their components has provided some of the most exciting advances in the field and definitely the tightest constraints on theory. Isotope cosmochemistry takes advantage of the fact that most elements have more than one isotope. Isotopes are just variations of the same element that have the same number of protons. That's what makes them the same element, but different numbers of neutrons. So they have different masses. These isotopes can separate or fractionate from each other within or among phases in a rock, or between a rock and its surroundings, or within a system due to chemical or physical processes that occur, for example, before, during planet formation, during planetary differentiation. And these can lead to measurable variations in the natural proportion of one isotope to another. Now, in the first example in the upper left, I'm showing mass-dependent fractionation. This kind of fractionation indicates that the amount of separation scales with the difference in mass between one isotope and a reference isotope. That probably sounds confusing. Basically, it means the separation of 44 and 40 is going to be approximately twice what the separation of 42 and 40 is, because the difference here is 4 and the difference here is 2. That's all you need to know. The variations are not large at all. Generally, we're talking about up to several parts per thousand. So really small, we need really accurate measurements here. Some meteorites also record variable non-mass dependent isotopic compositions. These are the so-called nucleosynthetic anomalies, which correspond to the isotopic signatures inherited from previous generations of stars. So before our sun. Only chondrites do this, as opposed to achondrites, because they preserve their discrete components that formed in the disk prior to the accretion of the parent body. Achondrites don't do this. They've melted, they've been processed. They don't have these discrete components anymore. And there are also unstable or radioactive isotopes and their decay products, but we're not going to talk about that tonight. My own work so far has concentrated on measuring mass-dependent, stable isotope variations in meteorites and mission-collected samples as well. And this involves, like I said before, crushing and homogenizing bulk samples into a fine powder, fully dissolving the powder in a combination of strong acids, generally hydrofluoric, nitric, followed by a step of hydrochloric, and then running the dissolved samples through a set of resin-filled columns using acids, the types, strengths, and timings of which have been carefully calibrated to isolate the element of choice, in my case, usually calcium. I then take the purified sample and measure its isotopic composition using a multi-collector mass spectrometer, which separates a sample's isotopes by their masses and charges, and then reports the data as isotopic ratios. Now, this is going to be the only plot I show here, but basically what we're looking at here is a plot of the 44 calcium over 40 calcium ratio in Earth. That's the gray bar in the center here, relative to all different kinds of chondrites and achondrites, as well as the moon and Mars. So this is just a really simple way of visualizing similarities and differences between extraterrestrial materials, and to help us draw conclusions that help answer the 5 primary cosmochemical questions. So building an increasingly comprehensive model of solar system evolution benefits not only from analytical advancements, like I was talking about with isotope cosmochemistry, but also on expanding the number of meteorites available for scientific study. More samples means more information, of course. And so in December, I set out on a month-long meteorite hunting expedition to Antarctica with an international team. Antarctica is one of the world's premier meteorite hunting grounds, and this is for two main reasons. The first one is that although meteorites fall in a pretty random fashion all over the globe, they fall at the same rate in Chicago as they do in Antarctica. The likelihood of finding a meteorite against a plain background like snow or ice is elevated. And so any rock that you see probably came from the sky. It allows for the recovery of meteorites without bias towards ones that look most different from Earth rocks, which would be a problem in Chicago. But equally important is the fact, is the geography and the weather conditions in Antarctica. They can create huge concentrations of meteorites. So firstly, really strong katabatic winds can concentrate meteorites, especially small ones, in topographical depressions like in valleys or at the bases of mountains and moraines. And we also get the formation of meteorite stranding surfaces. So the idea here is basically when meteorites fall onto the ice or snow, they eventually sink in and are covered in snowpack. But as the Antarctic ice sheet moves towards the margins of the continent, its progress is occasionally blocked by some kind of obstruction under the ice. And in these cases, old, deep ice with meteorites in it is pushed to the surface. It becomes stagnant. The meteorites that were under the ice are now resurfaced, re-exposed, and strong winds can blow snow away. And it leaves these accumulation zones where sometimes tens or hundreds of meteorites are found in a really small area, as one per square meter even. And this is why, although Antarctica makes up only 9% of the world's land surface area, over 60% of meteorite finds have been made in Antarctica. That's about 45,000 meteorites to date. Antarctica is internationally governed, and international collaboration is really at the heart of not only the continent's governance, but also in the expeditions, in the cutting edge science that happens there. And this particular expedition was a Belgian one. And it was a joint effort between the French and Dutch speaking universities in Brussels and the Belgian International Polar Foundation, which is based in Cape Town. The Belgians actually have a pretty long history in Antarctica. The Belgian Antarctic expedition of 1897 to 1899 was the first Belgian expedition and the first expedition to actually spend the winter in Antarctica. It was led by Adrien de Gerlache, who's pictured here on the right, and it's considered the first expedition of the sort of heroic age of Antarctic exploration. Now, unfortunately, the Belgica, which is the ship that they took there, was pretty poorly equipped, didn't have enough winter clothing for every man on board. There was a shortage of food. Everyone had scurvy. It was polar night for most of it. And they were trapped in ice 7 feet thick. But finally, after a few months, they managed to slowly drift down a channel that they opened up using dynamite. And it took them a month to move 7 miles. Eventually, they cleared the ice, and they made it back to Antwerp in 1899. So a success, but not without a lot of hardship. Luckily, since then, technology has improved a lot. Expeditions are very well equipped, much less risky. And our mission took place from mid-December to mid-January and took us to the Belgian Princess Elizabeth Station, pictured here, which is anchored on the granite ridge of Steinen Nunatak, that little mountain in the background, at an altitude of about 1,400 meters in the Droning-Maudland region of East Antarctica. It's about 120 miles, 220 kilometers off the northeast coast, and it's an ideal logistics hub for field exploration in the northeast of Antarctica. It's also a really good gateway to the Sor Rondana Mountains. and to glaciers and the Antarctic Plateau, great places to find meteorites. So thanks to its unique location, we did not need to travel far into the Antarctic wilderness to conduct our studies. So the station is kind of the brainchild of this rogue polar explorer, Alain Hubert, pictured here in the yellow. He's the founder and president of the International Polar Foundation. And with the support of private partners, he built and financed the construction of Princess Elizabeth in 2007, I believe. He became famous in the 90s for being the first Belgian to ever reach the North Pole. That was in 94. And for setting a world record for the longest crossing of the Antarctic in 1998. I think it was 99 days. I call him rogue because he did cause some controversy in 2017 when the Belgian state accused him of conflicts of interest and financial mismanagement and being careless with bureaucracy and being a little too adventurous with state funds. And so they forbade him access to the station. And as a reaction, he went there anyway and boycotted supplying a scientific mission to the station that year. So Belgium couldn't send any scientists in 2017, and it was a bit of a mess, but it's all been cleared up now, and he was very welcoming of us this year. The us being the 2022-2023 Bellaré team, Bellaré Belgian Antarctic Research Expedition Team, composed of Dr. Vincent Debaille, the team leader from the French-speaking University of Brussels, where I did my PhD, Dr. Maria Schoenbachler from ETH Zurich. We called each other the other Maria the whole trip. And as of last week, Dr. Ryoga Maeda, who was a grad student, joint grad student between the French and Dutch-speaking universities of Brussels, and me. So we spent about a week in Cape Town, just to go over logistical and cargo procedures, and of course to visit Boulders Beach to see one of the African continent's only penguin colonies, and this guy who I learned earlier is called a hyrax, I think. I don't know, South African mammal there. He's great. I love him. We also made sure to, of course, visit the Cape of Good Hope, where we had one of the worst hair days of our lives. And we also wanted to climb Table Mountain, but as you can see, the clouds are really sort of taking it over. They're really unpredictable, and climbs to the top get canceled pretty frequently because of that. So the Antarctic Logistics Center International organized and performed all of our flight missions, but getting to the final destination was, of course, expectedly still tricky. It involved first a 6-hour flight on an Ilyushin 76, which is an old gutted Russian cargo jet. Didn't feel the safest. That took us from Cape Town to Novo Station in Antarctica. And then after a short layover, we took a Basler utility aircraft to the Belgian airstrip. And then the final transport was over land with the world's first solar-powered vehicle specifically made for the Antarctic. So quite the process. On arrival, we got a tour of the facilities, the scientific mobile laboratories, the power generation facilities, the vehicles, and we were allocated dorm rooms. This is the one I shared with the other Maria. I got top bunk, of course, because it's more fun, obviously. But you can see how small the room was. It was quite the exercise to try not to keep each other awake with our snoring and to manage to fit all our bags in there. And on the left, you have just a tour of the main entrance of the building. Now, what's really cool about the Princess Elizabeth Station is that it's the world's first zero emissions research station. Solar panels cover most of it, and the panels feed the smart grid at the station with electricity, while any excess production is stored in batteries. There are also wind turbines to harness the massive katabatic wind energy, and they're designed to withstand some pretty vicious storms if necessary. There are also thermal solar panels used to melt the snow and heat the water that's to be used in the station's bathrooms and kitchen. And the building is actually so well insulated that no heating is used. And so the station is technically classified as a passive building. I also find it cool that there are bioreactors that use microorganisms to neutralize the wastewater so that it can be reused. We underwent about 3 days of basic training, and this included skidoo driving and maintenance, crevasse rescue, hypothermia reversal, first aid, CPR. Incidentally, it's awesome being inside a crevasse, but only in a controlled situation, of course, only when you know you're being rescued. But it's so beautiful down there. And this is us having mastered the art of the skidoo. Incidentally, I do not drive. I have not driven a vehicle in the past 5 years, but I do love riding the skidoo now. I'm a skidoo master. It's a bit loud. So after 3 days, we packed our sleds and drove about 3.5 hours to the spot chosen for base camp. And this is an area called Niels Larsen-fjellet. So we set up our tents, got comfortable, and began the meteorite search the next day. So where we decided to search was not random. To aid in the planning of the expedition to help us decide exactly where we were going to look for meteorites, we used the results from a paper that came out last year describing the use of machine learning to create a probability index, or a treasure map for Antarctic meteorites, if you will. The analysis showed that we can predict meteorite-rich areas using observations on surface temperature, ice flow velocity, surface cover types, surface geometry, and these factors all need to combine favorably in order for us to find meteorites there. There's always been a human factor involved in meteorite recovery missions, but it's just not possible to evaluate the potential of an entire continent, especially one as big as Antarctica, by relying solely on human judgment. So machine learning is pretty exciting here. We can find the likeliest places to find meteorites, places that have already been visited, places that have never been explored. A lot of these are close to Princess Elizabeth. So it was pretty exciting for us because the calculations in this paper suggest that more than 300,000 meteorites are still waiting to be found on the surface of the ice sheet. And these new recovery techniques could represent a shift in how Antarctic meteorite recovery missions are conducted. So for the next few days, we performed searches of moraines north and south of the Niels Larsen-fjellet, and the searches were performed on foot, with the team members spaced about 10 to 20 feet apart in a line, doing these systematic sweeps back and forth in a given area. However, after a few days, the searches yielded no meteorite finds. There are plenty of meteorongs. These are dark-colored rocks that, because of their color and texture, fooled us into thinking they were meteorites until we examined them more closely. And actually, we saw a lot of rocks in the process of disappearing into the ice. These are called cryogenites, where rocks absorb heat from the sun and then re-radiate this heat to their surroundings, causing the ice and snow around them to melt and for the rock to sink into the snow or ice. We expect this for dark-colored rocks because they absorb more heat, but we actually saw them around light-colored rocks too, as you can see in the movie, and silt patches. We saw a lot of liquid water, and we saw rocks sinking into the ice at a faster rate than we expected, perhaps hiding any meteorites we could have found. And I won't lie, by Christmas Eve, this was getting depressing that we hadn't found anything yet. So we made ourselves feel better with some cheese fondue and a gift exchange. Although I didn't get the gift exchange memo, so I had to spend the next day writing limericks about everyone to make up for it. But on Christmas Day, we decided to carry out a search in a blue ice field that was dilute enough with rocks that doing it by snowmobile was actually the more efficient way. And so we drove very slowly, about 5 to 10 kilometers an hour, in a V formation with the field guide at the front and with 2 people on each side, so that both sides could be checked. And after several hours of driving, we happened upon a small, dark brown rock with a black fusion crust. It was about 170 grams, and Vincent performed a magnetic susceptibility test right there in the field with a pocket-sized instrument meant for quick field identifications. And the measurement indicated that we were looking at a meteorite. Throughout the day, we would find two more, both pretty small, each about 30 grams. And in every case, we would collect them in plastic bags, avoiding direct contact with our hands. We would give it a provisional name. That name was written directly on the ice with a special pen. We took GPS locations. Yeah, it was a Christmas miracle on that day, for sure. The next day, we explored the moraine of an ice tongue. An ice tongue is essentially a floating platform of ice attached to the front of a glacier and extruding into a basin. The weather was actually so perfect that day that I could take off most of my coats and my gloves, and we enjoyed a long lunch break, just sort of sat around enjoying the weather. But the terrain proved very difficult to search for meteorites on because, as you can see, there were so many of them, and most of them are dark in color. So picking out the meteorite was just not easy. Although at the very end, just as we had turned around to go home, we did manage to find another small one, about 30 grams. After that find, we had to pack up and go back to the station for about 5 days because the weather was getting really bad. Here's just the view out the window of the station. The storm was like this for 5 full days. Certainly too bad for field work. The snowdrift caused by the really high winds led to a 10-foot pileup of snow in front of the station's main door that we had to spend days digging ourselves out of. And the snow was also covering the solar panels. It was really important to get those uncovered so that we could keep making power for the base. And visibility was so low that it was called whiteout conditions. We really couldn't do any research for a little while. But once it did clear up, we spent the next 4 days around the Nansen Blue ice field, which is about 60 kilometers, 40 miles or so south of Princess Elizabeth. And pardon my Norwegian here, but we studied areas of Verhalenfjellet, the aligned Nunatuks, and the Roysen Nunatak. And one of those days we actually just spent on a mountaintop collecting sediments for possible micrometeorites using, as you can see here, a very high-tech dustpan and broom. And then we would take those sediments back to the mobile science containers and sift them for anything less than 2 millimeters in diameter and making aliquots for each team member to take back to their institution. So the weather looks nice here, but in reality, the weather these last 4 days was really rough. It was much colder than usual. The terrain was really difficult. As you can see, this terrain has a lot of sastrugi, which are hardened snow dunes. And it's just low visibility. On some days, you couldn't tell the difference between the sky and the ground. They were the same color. And to make matters worse, I fell off my snowmobile at some point, injured my shoulder. It was a brutal last 4 days, and we were all kind of wanting to go home at that point. But in what was to be the last hour of the last day of our search, we stumbled across an enormous brownstone sitting by itself in the middle of the ice. And it was a little bit smaller than a bowling ball, but about twice the weight of a bowling ball, so fairly dense. And it had the telltale black fusion crust surrounding it, although, as you can see here, some of it had started to wear away. We performed a magnetic susceptibility test on it right there in the field, and it indicated that we had a chondrite on our hands, likely a subtype called an H chondrite. So the week had felt vindicated. We were so excited to find this massive sample. Oh. The field guide stood by as the rest of us took pictures with the rock as if it were a celebrity. And to be honest, it kind of is. At 17 pounds, it puts the meteorite in the top 100 heaviest meteorites ever found in Antarctica. We were really pleased with this find. Right after that, we put the recovered meteorites in the food freezer at the station, and this was so that any snow that had accumulated around the rock did not melt. We didn't want it to melt because then you would risk liquid water seeping into any cracks and altering the minerals. We don't want that. Then it was transported in a frozen state to the Royal Belgian Institute of Natural Sciences to be thawed in a vacuum environment. And it's going to be classified and characterized there initially. And I hope to bring it here on some sort of rotating display. That'd be great. But what am I doing right now while that's happening? Well, I'm going through all of the sediments that I brought back. I brought about 10 pounds back with me of sediments. And I have an intern now for the first time, and he's going through the sediments to try and find micrometeorites in them. He's found about a dozen so far. And I am interested in micrometeorites because so many more micrometeorites fall to Earth than meteorites. Again, 47,000 tons of it. And because so much more falls, they really provide us an unparalleled sample set for studying chemical variation in the solar system. And again, because there are so many more micrometeorites than meteorites, they may even contain information different from information contained in meteorites. They may even sample parent bodies that we haven't sampled yet with the meteorites in our collection. So that's why I'm interested in micrometeorites. So what did we learn? I think initially we were a little disappointed coming back with only 5 meteorites. Granted, one was very big. But when you remember that this was sort of a pioneering mission to search areas that hadn't been searched before, to explore new potential meteorite stranding zones, I'm pleased. I think my main takeaway from this is that machine learning is very useful, but perhaps only to a first order. Actual visits to the predicted accumulation zones are still required because you're going to have all these local factors such as topography, wind direction, maybe even the loss of meteorites to cryogenites. You're going to have all these things complicating the search. So definitely still necessary to back up machine learning with real visits still, which I don't mind. And yeah, if anyone has any questions, I'll be happy to take them.
You have a lot of questions, so we're kind of coming in as you've been talking about your wonderful adventure. So we'll go ahead and get started. I'm going to put 2 together. One is how can you tell a meteorite versus not a meteorite? And when the glaciers also pick up the bedrock as they're kind of going through that cycle of, the wind and the water pushing it toward the coast.
Yeah. So I would say the first couple of days that we were there, it was kind of difficult to pick out a meteorite from the rest of the rocks. And I felt a little embarrassed. I was like, I do this for a living. I look at meteorites all day. How is it possible that I can't find the meteorites here? But it takes a while for your eyes to adjust because everything there kind of looks like a meteorite at first glance. Everything is dark colored. Everything is kind of shiny. Everything kind of has a similar texture. So it takes a few days of eyes adjusting. But once you do, you're really looking out for this fusion crust. And actually it helps if part of it is wearing away a little bit, like on our big one, because then you can tell it's actually a crust. You can tell that there's something underneath it. That's the first giveaway. The shape is also kind of a giveaway. It's usually a little bit rounded. Sometimes there are these thumbprints almost in the crust. They're called regmaglets. And they develop from the melting of the meteorite as it enters our atmosphere. You can also do magnetic susceptibility tests, but to be really, really sure, you do want to bring it back to the lab and start doing chemical analyses.
I might ask you again. I'm going to combine a couple of different questions because they're kind of similar. So I have a couple of people wondering, how cold was it at your base camp and how would you compare Antarctica to Chicago winter?
So it was polar summer down there. So it was warm by Antarctic standards, maybe about like minus 10 or so Fahrenheit. And for the most part, it was fine. We wore many layers. I think I was clocking in at 7 or 8 layers at some point, one of them being a giant full body onesie. And I heard, because I was in kind of contact with people through satellite phone occasionally, I heard that it was colder in Chicago than it was in Antarctica over Christmas time. I heard it was about -20 or 30 here around Christmas.
Yeah,
And that's a little unfortunate for people stuck here because I was living it up in tropical Antarctica.
wow. Well, at least you were warmer.
Yeah.
So we know that you had to go through the training for, for survival, or in case you ran into some kind of emergency. What was kind of surprising to you in that training, or that you felt like was the most valuable? Because I know that you're in a hostile environment, or like an environment that, if something happens, it can happen quickly.
Right. Yeah.
So, yeah, well,
I guess for me, learning hypothermia reversal seemed like the most imminently important because I knew we'd be spending, 8, 10, 12 hours outside, which, it really feels fine for the first couple of hours. But imagine being outside in Chicago on a -10 day for 8 hours. Like it does become very uncomfortable eventually. And just taking off your glove for a minute results in huge pain. And so I knew that there was risk of hypothermia. I knew that there was immediate risk of that. So learning how to isolate someone from the ground, learning in what order the layers are supposed to be packed, that was really important. I was also really scared of falling into a crevasse. Our field guide had lost his best friend to a crevasse the year prior, and I knew that some of the areas that we'd be searching were pretty crevasse heavy. And I guess for anyone who doesn't know what a crevasse is, it's when, as the ice sheet moves, you can think of the ice sheet as fabric almost. If it hits topographical interference, it'll rip essentially like a fabric, and it'll infill with snow, but not all the way. It's deceptive. It's actually hollow down here and just covered with a small snow bridge up here. So you think it's fine to drive over or walk over, and then you fall 90 meters onto solid ice. It's really dangerous. So I was very scared about falling into a crevasse. So learning how to drag someone out using different methods, how to harness myself, how to work with the others to get myself out. That was really important.
oh, that would be scary.
Yeah.
I don't even want to think about that.
Yeah.
Oh my goodness. Does exposure to geological pressures and processes alter contracts at all?
Yes. There's actually a whole subfield, or subfield, I guess, of people who study the alteration of chondrites and other meteorites once they fall to Earth's surface. As soon as they land on our surface, as soon as they enter our atmosphere, they're changing from their initial compositions. Our atmosphere is mixing with their composition. Our ground is mixing with their composition. And if it rains, the rain is messing with their composition. So teasing that apart from their initial compositions is really important. Definitely a field that requires more work.
So somebody asked, are you afraid that using some of the processes that you're using to analyze samples prevent future generations from evaluating some samples with more advanced methods later, because we wouldn't be able to replace
Sure.
that sample?
Sure. Yeah. I guess they're referring to destructive analyses. We never use the whole sample because indeed, technology moves really fast, and we never know. In 5 years, there might be a way to answer all the questions we want to with, 20 grams that we have left of this meteorite or something. So we do try never to use the full sample. And if there is only a very small amount left, then we stick with non-destructive analyses.
Silly question. Do poles have any effect on concentration of meteorites that fall in Arctic regions? I'm gonna read this verbatim. My brain started wondering about some sort of cluster effect bias or something like to that effect.
to my knowledge, it does not. To my knowledge, meteorites fall evenly across the whole Earth, and there's no effect from poles.
Right. Can you tell us a little bit more about the micrometeorites? I know that you were joking around about dusting them up on a dustpan to, kind of collect. But how do you, when you're ciphering through them, like how do you tell that they're the actual meteorites?
So initially, you don't know. Initially, the only analytical facilities or tools that we had available to us were a sieve of 2 millimeters and some wax paper. So really all we could do there in the containers was sift for any sediments that are large, that are smaller than 2 millimeters, and throw the rest away. And that's because we make the arbitrary cutoff for micrometeorites at 2 millimeters. Anything above that is a meteorite. And in that case, we'd just be able to pick it out anyway. But that's why I came home with 10 pounds of sediment instead of just, a dozen micrometeorites. It's because now we have to do the hard work. Now we have to look through each of those grains under a microscope and check for textures that are indicative of micrometeorites. So that's what I have my intern doing right now.
Um, so from Lynn, I was told by a friend who recently visited Antarctica as a tourist that scientists use the time zone from their home countries. Is this true? And if so, how do scientists from different countries work together in different time zones?
Man, this freaked me out when I got there because so I was in Cape Town for a week, and that's I think right now 7 hours ahead of Chicago, or 8. And looking at a map, it occurred to me that where we were going in Antarctica was probably 1 hour ahead of that. So I was planning on being 9 hours ahead of everybody I knew in Chicago. And then we got to the Belgian base, and it was Belgian time. So they operate strictly on Belgian time. And the reason this is really confusing is because the nearest bases to the Belgian base are the Japanese station and the Russian station, but we all operate on different time zones. It doesn't make any sense, I guess, because there's very little contact with the outside world. And the only people you would have contact with are probably from your home country. I guess that's why, but no, it doesn't make any geographical sense.
Yeah, that's interesting. When analyzing the elements within a meteorite, that they are meteorites, are they ever challenged? Is the composition ever so similar to the composition of Earth rocks that the results can be inconclusive?
Yeah, I guess in the beginning, before analytical techniques advanced to the state that they're in right now, things were pretty inconclusive. But as our analytical techniques improve, we can make higher and higher precision measurements that show that, no, indeed, we do have, 0.2 parts per million difference between the oxygen isotopes in this Martian rock and this Earth rock. So we're getting pretty good at it. Sometimes people still do disagree on exactly where in the solar system something came from, but generally we can tell it's not from Earth.
Oh my goodness. What exceeded your expectations about the expedition? What other questions have opened up for you now that you're back from your personal research?
What exceeded my expectations? I think I exceeded my expectations. Does that sounds really full of myself?
No,
But
first of all, like you're going over crevasses and you don't even know. I'm, I just
it was scary, man.
Yeah, amazing.
I had never done field work before. I was a lab rat through and through. I spent all of my time in a white bunny suit in the clean lab over there doing chemistry. And so when I was propositioned for field work, I was really scared, especially in Antarctica. That's going from 0 to 100 really fast. And I was terrified of the cold. I was terrified of skidoo driving. I was just terrified of braving the whole thing for a month. But yeah, we all pulled through. I pulled through. There are 2 other team members who hadn't been there before. We all pulled through, and I was just amazed at our resilience and how positive we all maintained ourselves the whole time. That was great. What new questions have opened up? Man, I guess I'm still trying to answer those 5 main cosmochemical questions that I posed before. I would love to have more and more samples and hopefully ones that I collect myself, It's exciting.
Well, I'm in awe, like I said, because yeah, I don't like the cold. So and I live in Chicago. It's amazing. Before we get to, we'll do a couple more questions, but before we get to that, I just want to mention a couple of member events that are coming up. First Kings of Europe will be opening up later this month, and we have member preview days on Wednesday, March 29th and Thursday, March 30th. First Kings of Europe opening event and discussion will take place for members and donors Tuesday evening on April 4th. And of course, we're super excited that we are going back behind the scenes for members nights on Thursday, April 20th and Friday, April 21st, where you'll get to speak to our scientists and scholars and learn about the different projects that they're working on. And again, with your membership and your gifts, support and enable them to do. So please join us for any of these upcoming events. We'd love to see you here at the museum. I'm going to ask this question just because I'm curious too, but if I took a sample of dirt from my backyard, what are the odds of there being micrometeorites in it?
Oh my God, high, really high, actually. I would say don't go to the dirt, go to your rooftop. Go to your
Okay.
rooftop and maybe check your gutters. You'll find some micrometeorites. It'll take a while. You'll have to sift through a lot, but like you will find micrometeorites.
I'll
I
just bring it
think,
to your intern.
yeah, bring them over here. We'll do it.
I'm kidding.
I think I love micrometeorites because they're such a great reminder that we are just a rock ball floating through space, collecting space garbage. Like we're not that special. I think it's just a great reminder that we're part of something much, much, much larger.
Oh my goodness. And then we do have a request if you could share some books or some links, about meteorites and studying meteorites that, that we could share with our
Yeah.
members and donors. That would be great. We can send that in a post email
Yeah, sure.
to them. So we'll go ahead and get popular science books about meteorites or websites where you can learn more.
Sounds good.
That would be great. And we have a couple more questions, but I think, we'll try to get to those a little bit later. Again, thank you everyone for joining us tonight. It's, always a pleasure for us to bring the work of such amazing, staff at the Field Museum. I live vicariously through expeditions like Maria, because like I said, I would not be going to the Antarctic, and kudos to you for doing it. I know you said that you were surprised in yourself. I think that just shows that you went with it and you were a lot braver than a lot of us. So thank you, Maria, for joining us tonight.
Thank
you to
you.
our Field Museum members and donors, and hopefully I will see you at the museum soon. Take care, everyone.
Thank you.